a few people coming from far away at this conference. Yeah, you is one of them. Actually, it's not your first time attending. Second time, yeah. And so it's great to have people from all over the world come and share with us what they do in understanding botnets and fighting botnets in real networks is your main topic. Detecting and blocking and tracking botnets in the networks. So I guess we should start. You ready? Okay. So you have the floor. Thank you.
Okay. My name is Ya Liu. My talk is called Improve DDoS Botnet Tracking with Honeypots. I come from Qihoo 360, and I do malware analysis and botnet tracking. This is the agenda. Firstly, I will talk about our DDoS botnet tracking and explain what problems we want to resolve. Secondly, I will talk about the connections between the botnet families and the PGS. Here, the PGM is the packet generation algorithm. Thirdly, I will talk about the backscatter collection and analysis techniques. The next part is the core of our approach. It's called the PGA analysis. And the final part is about our experimental results. Basically, DDoS botnet tracking is aimed to learn botnet-assisted DDoS attacks in real time. Now, such information is often called threat intelligence, and it helps better design better detection and mitigation solutions. And for example, we can stop a DDoS attack by rendering the C2 controllers offline. As for the exact information, it can be summarized into 4W. It means who is being attacked, by what botnet families, under which C2 controllers, with what set of attacking parameters. As you can see in this picture, there are real DDoS attack commands tracked from Morai botnets. Here is a summary about our tracking work. We started our work in 2015, and now we can track over 30 botnet families, including the Morai, XR.DDS, Elknot Belgates, and other common DDoS families. And in the past 2 years, we have successfully tracked over 6,000 botnet families. From them, over 800 million attack commands were received. And from those commands, we checked about over 250,000 attack targets. And our data has been shared many times with colleagues outside of our company. Yes, to improve our tracking work, we continuously update our system in terms of the supported botnet families and the C2 controller numbers. And we also need to do evaluation purpose. So we need to know what family unknown botnets are active in the wild, and what family no C2 controllers are outside of our tracking list. To answer the two questions, we need information about the real attacks, and we need a method to connect them to the used botnet families. As we know, the real DDoS attack information is often mastered in the hands of anti-DDoS vendors or cloud service providers, and for consideration of customer privacy or business competition, that information is usually kept secret and cannot be publicly shared. So we need another technology to know the real attacks. Fortunately, there is a technique called DDoS backscatter. It's generated due to the use of spoofed source IP addresses in the attacking packets. For example, in case of TCP SYN flooding, if a victim receives a spoofed SYN packet, it will acknowledge that spoofed IP with a SYN ACK packet. It's actually DDoS backscatter is known as a important cause of dark space traffic in parallel with scanning and network misconfigurations. It has been studied for a couple of years, and dozens of solutions to detect and monitor DDoS attacks based on backscatters has been proposed in the past years. There are two techniques can be used to collect the dark space traffic. They are darknet and honeypot. A darknet is designed to monitor the traffic destined to a block of unused IP addresses. Since there are no normal communications there, so all traffic destined to that address space can be sorted as suspicious. And the purpose of darknet is that it can collect a large number of packets destined to a block of unused address at the same time. The cause is that its deployment is non-trivial. It mandates the deployment of a network device, such as a router, to inject the route to the unused address space into the internet. Compared with darknet, honeypot is more cost-effective and easy to deploy. The cons is that it can only collect packets based on single IP address. And if you want more traffic, you have to deploy more honeypots. In our scheme, we use our low interaction honeypots to collect the dark space traffic. We have deployed about 30 low interaction honeypots all over the world. And we take 4 traffic capture on each of them. Since there are normal honeypot software runs on the honeypot, so we design a special mechanism to separate the wanted traffic from the unwanted. Here, wanted means traffic generated by the honeypot applications, and the backscatters can be classified as unwanted. And as we know, in modern DDoS botnets, attacking packets are usually generated by the bots from the ground up according to some specific algorithm, which we call PGA, and then sent to the victims with raw sockets. So there are some obvious, for example, there are some obvious PGA attributes. The first is it's attack type specific. For example, the PGA for TCP SYN flooding is different from the PGA for DNS query flooding. The secondary is that PGA is often family specific because PGA code is usually not shared across different botnet families. The third and the most important attribute is that common PGAs are usually imperfectly designed or implemented, which leads to fixed patterns in the generated packets. It means we can identify botnet families by their PGA signatures. To better show this problem, I will show you 2 examples borrowed from the recent leaked Marai source code. The first is Marai's PGA was called Stomp attack. From the code in the circle, you can see the function of hot to net short is wrongly used here. It will truncate the 4 bytes of sequence number and acknowledgement sequence number into 2 byte ones. which leads to the fixed patterns in the TCP sequence number and acknowledge sequence numbers. The second is Mari's PGA for the called GIE ether attack. As we know, GIE is basically is a tunnel protocol. It has the inner IP head and the outer IP head. Here you can see that the inner IP headers identification and the destination address fields are separately derived from the outer IP headers identification and the destination address, which leads to two bounds relation here. From the two examples, you can see that both bug implementation and design flaws can lead to PGA signatures which can be calculated by the packets. On the other hand, PGA signatures can also be concluded by reverse engineering the bot samples. So it's possible to correlate the DDoS attack to the used botnet families by PGA signature matching. This is our architecture overview of our approach. The key steps include separating the unwanted traffic from normal honeypot traffic and extracting DDoS backscatters from the unwanted traffic, a spike-based attack detection, the PGA analysis, and the signature matcher. Here, the labeled signatures are manually concluded from the bot samples. In the first step, the unwanted traffic is separated according to the honeypot software logs. And in the second step, the DDoS backscatters are extracted based on packet type. I will talk in detail in the later slides. And we use a spike-based mechanisms to detect the DDoS attack. As you can see in this example, this is a real TCP flood attack. It is provided by our network data. The target is shown in the above circle. And in this picture, you can see an obvious spike, which lasts about nine hours around this time. Because the spoofed source IP addresses were used in this attack, and our honeypots received their backscatter traffic. There is also a obvious spike in the backscatter traffic, and its peak time is very close to the previous one. So this is our spike detection scheme. Firstly, backscatters are subgrouped based on the packet type, source IP address, and source port. And in case of DNS responses, the situation is a bit complicated because, for example, in case of DNS random subdomain attacks, a large number of queries are flooded to the open resolvers. And if we receive such a backscatter traffic, the source IP addresses will point to the resolvers. But the real targets here are the query domains. So we also support to subgroup the backscatters based on the query domains. And the subgrouped backscatters are further used for spike detection according to the three policies. The first policy, the packed in time interval, is used to subdivide the backscatters into different spikes based on their arrival time. And the obtained spikes are further filtered according to the third and the second and the third policies. It means only those spikes with enough number of packets and collected by enough number of honeypots are used for further PGA analysis. We do this mainly for consideration of low positive in PGA analysis. Now we support three kinds of backscatters. The first is TCP SYN ACK. The second is DNS response. The third is SMP unreachable message. It means ISP type equals to 3 and code equals to 3. And for this message, we are only interested in the reflect TCP SYN packet and DNS query packet. Our PGA analysis is based on the attacking packet fields. They are recovered from the backscatter packet. For TCP SYN ACK packet, we can restore the source and destination IP address and port, the initial sequence number. For DNS response, we recover fields of source and destination IP address, the source port, the transaction ID, and the query domains. And for SMP unreachable message, we only extract the reflect SYN packet and the DNS query packet. This is the core of our PGA analysis. We define two kinds of vectors. The first is packet feature vector. They are used to, they are defined to find the fixed patterns in the attacking packets, and furthermore to calculate the spike feature vector. The vector is constructed for each packet in a single spike. For TCP SYN packet, a 16-dimensional vector is defined. It composes field bytes from the source IP address, the destination IP address, the initial sequence number, the source port, and the destination port. For DNS query packet, the vector has 12 dimensions. It composes of field bytes from the source IP address, the destination IP address, the source port, and the transaction identification. This is a real TCP SYN packet feature matrix. Each line for consideration of page size, only the first 21 packets are shown here. Each line represents a single packet feature vector. And since the source IP addresses are used by our honeypots, I masked the first 3 octets of them. And in this matrix, it's very easy to see there is fixed patterns in the lower 2 bytes of initial sequence number. And except the fixed patterns, we also want to find the boundary relations as we seen in the previous Marai example. So we define the spike feature vector. It's obtained by calculating the Shannon entropy of each column of the packet feature matrix. The theory behind this definition is that if there is a boundary relation between 2 fields, then their corresponding elements in the spike feature vector should share the same value, or at least have very close values. And if 2 spikes are generated by the same family of PGA, then they should have very close distance. This is a real DNS spike feature vector shown in the below picture. It's derived from the above matrix. From the spike feature vector, it's very easy to find the 2 boundary relations. The first boundary relations exist between the 3rd and the 12th column. we can see that the third octet of source IP addresses is equal to the lower byte of transaction ID. The second boundary relation is that exists in the 4th and the 11th column. We can see the 4th octet of source IP address equals to the high byte of transaction identification plus 1. And this is a spike clustering and PGA profiling. PGA spike clustering is to find the similar spikes that are probably generated by the same family, and it's also defined for consideration of scalability. And now PGA is profiled in 2 ways. The first is the fixed patterns are detected by checking element of 0. The second are bound relations are detected by checking the same elements in the spike feature vector. And the profiling result is used for signature matching. It's worth noting that the repeatedly mentioned word of bound actually means one field is derived from another one. It can be shown in this formula. And the simplest bound relation is just byte sharing. But the real situation is, I think, is very complicated. So our approach only detects whether there is boundary relations between different fields, but the exact relations are left for manual analysis now. And with the PGA analysis output, the evaluation about our tracking work is done in 2 ways. The first is if a detected spike is not successfully correlated, it means that there are family unknown botnets in the wild. And if a spike is successfully correlated, we just check out our tracking list to see whether such an attack has been tracked or not. This is our experiment result. Totally 2,333 thin ACK spikes and 1,835 DN spikes are checked from the backscatters received from last August to this October. And from them, 4 large PGA clusters are found. And the first cluster means thin ACK class 1 has the largest number of spikes. And we successfully connected to the XR DDoS botnet family. And the rest 3 clusters have not been successfully connected to any no families. It means we need to need to find their sample in the future. It's worth noting that the DNS class 1, class 2, this one, yes. Actually, all the work presented here is inspired by this class. Now we can, now what we know about this class is that it can be connected to a family unknown attack tool, which supports the DNS random subdomain attack. As you can see this picture. The red colored domain is a real attacker, and the prefixed subdomains are randomly generated. And our studies show that this class shares the same subdomain pattern with elk, not Bill Gates. It's another in another botnet family, but it has different PGA signatures. As you can see, this table. And this attack tool is still inactive now, but you have not seen its sample. If you know some information about the family, or tell me, please. That's all. Here is the conclusion. Basically, I present a solution to connect the real DDoS attacks to the used botnet families. The detailed solution include a backscatter collection scheme with honeypots. Our scheme can make full use of the end honeypots and a spike-based attack detection scheme from the extracted DDoS backscatters and PG analysis approach based on recovered attack impact fields. Since our work is still ongoing, we want to improve our work in the future in the following aspects. First, we want to consider the DNS random subdomain patterns in PG analysis, such as the subdomain length, the chassis, and the chassis. And we want to support more types of backscatters, such as TCP reset packets, and some unknown UDP application packets. And now our labeled signatures are mainly concluded by manual reverse engineering the bot samples. We want to automatically learn the PG signatures from samples or from the attacking traffic in the future. That's all. Do you have any question?
Any questions? Right. He's coming in. Stop. He's here and he's coming.
Thanks for the presentation. It was great. I'm Arthur from Cyber.com. I see that you're monitoring Mirai. Can you tell us a bit more about how this botnet is being currently used and what kind of targets are being used for Mirai? And what is your opinion about the actors that are using this botnet?
Thank you for your question. I think it's better we can talk about this topic offline. Okay.
I'm happy to find you.
Yes, actually, we have tracked many Mirai botnets in the past months, but I think it's not suitable to talk that question in this case, right?
Okay, because I've seen there's just 8 of them active now, and they are not very,
You might remember, it's over 12. Over 12. Yes.
Okay.
Hi. Can I ask you just one question about, have you did some behavior-based experimental work with botnet detection?
Behavior-based?
Behavior.
What behavior? Host behavior or network behavior?
Instead of signature-based, if you used the experimental work, you did
our signature is concluded. Our signature can be concluded either from reverse engineering the samples or reverse from the attacking packets. I mean, no behavior here.
So you didn't work with
yes,
behavior?
It's either from the reverse engineering sample or control from the attacking packet fields. Yes, no behavior here.
Good.
Thank you.
Okay, thank you.
One more question? Come on.
Thank you.